I want to start off with a few announcements. One is that the material for this workshop and all the other workshops in the series is available here. No, wait, do I have a way to put it in the chat? No, I don't have a way to put it in the chat. So QR code works. The link is, not too long. So all the material, again, all the material that I'm going to cover today and for the rest of the workshops throughout the year is going to be available here. I had meant to actually link to it, but then I didn't get around to it, but I will try to do that after today's session. So we're in the data science workshops part, and so the schedule for that is here. I'm not sure why there are two links. I do know why there are two links. So today is the 21st, I think. And so we're going to be talking about reproducible research, which is good because that's what I was planning on talking about. The next announcement that I need to make is, I'm going to put up this slide. Make that a little bigger. Now I got the annoying stuff there. Hold on. Okay, I'm going to separate this. Make it full size, and then that's good. If you are here, either in person or on Zoom, please sign in. So this is, we're not doing this to I don't think to hunt down people who aren't here, but we are doing it because this workshop series is available to you all through a grant from the National Institutes for Allergies and Infectious Diseases. And, we want to show to them that there are actually people showing up and we're not just using money to, I don't know, sit around and watch cat videos or something. So please sign in so that we have that information for our reporting back to the National Institutes of Health. I see there are questions in the chat, but okay, good. I don't think I can actually, oh no. Are you controlling it or is Jim? Okay, good, thanks. And then the last announcement I think I have for now is that I'm aiming to, some people are here in the classroom, some people are here on Zoom. Oh no, I have two announcements. Some people are in the classroom, some people are on Zoom. It's obviously a little bit easier for me to see the people on Zoom. But if you're, the people who are in the classroom because they're right in front of me. If you're on Zoom and you have a question, please, you can put it in the chat or you can just yell. And if I don't notice you, please feel free to yell or put it in the chat again, and I will try to keep an eye on that. And then the last announcement is, because I know that it's especially painful staring at a Zoom screen for extended periods of time, I'm aiming to stop every hour. So I set a timer on my watch to stop around 2 for a 5-10 minute break, and then we'll stop around 3 for another 5 or 10 minutes. Okay, so I am Josh Granick. I'm here to talk about reproducible analysis. So the first part of today is going to be, I'm going to give a lecture about reproducible analysis to just kind of give you a feeling for what it is and what I think about it. And then the second part of the day will be an introduction to using Git for version control. If you don't know what I mean by that, hopefully by the end of by the end of the lecture, you'll have some idea, and hopefully by the end of today, you'll have an even better idea. So I think I can get started. Does anyone have any questions or anything that they want me to? Yeah, go ahead.
So
Oh, actually, I'm going to ask for people in the room, if you have a question, what do you do? If you can push the button on the mic, then the people, it'll turn green, and then people on Zoom can hear you, but I'll try to remember to repeat them. If not.
Okay, yes. So I just wanted to ask, the link that Kelly shared with us, is that what we're going to be using on the...
Do you know which link she shared? I'm not sure. I get lots of emails from Kelly, so so I'm not sure which link it was. I'm guessing if she shared a link, it's either for the course material, for the Zoom, for the sign-in, or for the the end of the session feedback thing, and maybe all of the above.
ECC on demand.
So that's for the, so I was wrong. That's for the computing environment that we're using. So we will use that for the second half of today. But probably we're not going to get to it until definitely after we break at 2 and maybe probably closer to 2:30. So we will be using it, but not yet. And if actually she probably asked you to be sure that you could log in. And did anyone have any problem logging in? Anyone on Zoom have a problem logging in? Great. Always good when that works. Usually it works, but every once in a while there's a problem. Okay, other questions before I start talking about reproducible analysis? Okay, so this is reproducible analysis is something that I'm very passionate about. And I have the slide to remind me. This is for me. I'm not going to explain at all what I'm doing right now. I will explain later. But for now, because it's hogging the screen. No, didn't make it all the way. So for now, you should probably be completely most of you will have no idea what I'm doing, and that's fine. Like I said, I'll explain later. There's a little bit of magic going on. And this one. That's not working, right? Come on, there. Is it working? Okay, cool. Okay. So like I said, we'll get back to that later. So let me give you a little bit of an overview. Oh, and I have another interruption for myself. So I have a short poll before I even get started to see what people know about reproducibility. And I guess I should have that there. And I think it should work. Where did I put the other one? Sorry, I'm just gonna. That's not what I wanted to do. So why can I not see? I am getting responses. Okay, cool. So I'm going to give people maybe 15 more seconds to do this. Anyone need longer? I just don't want to sit here and wait while
I accessed the link, but it says that I'm waiting for you to the presentation to begin. Yeah.
Now mine is there. I swear it was.
Thank you.
I looked a second ago and it was activated, but thank you. it will not be the last time today I do something stupid. And I think it first asks you to like sign in or something. You don't have to do any of that. You just do skip. I can't, somewhere it shows me how many people have actually responded, but I can't remember where that is. Does anyone need more time?
One question?
Yep, just one question for now. Nobody needs more time? Okay, so here are the results. Is it actually showing everything? Yeah. So that's helpful. I'd probably put myself in D2. I aim for E, but I'm not perfect. So good, like about half of you work reproducibly, and everyone's heard of reproducible research. So that is helpful to know. Come on. Okay. Now where do I get my cursor there? Okay, so I'll tell you what my opinion, and I'll say this now and I'll say it probably again several other times. You know, opinions will vary about what reproducible analysis is and you know what standard to aim for. So this is my opinion. I think I have a reasonable opinion, but you know, not necessarily. And when I looked for a definition of reproducible analysis when I was putting this talk together several years ago, I couldn't find something that I was really happy with. So I just came up with my own. And so my definition is that reproducible analysis is an important part of reproducible research. Reproducible analysis requires that, and obviously it's the analysis part, reproducible analysis requires that all the components of the analysis be archived in a way so that anyone can independently repeat the analysis and arrive at exactly the same results. And so, again, this is my definition. Other people might have other definitions, but I want to talk about the word anyone, which is somewhere there in italics. Who do I mean by anyone? I guess, of course, that can mean anyone, but I'm actually thinking of specific people. The first group of people is lab mates or group mates. I know that it is not uncommon for me, I mean, definitely like throughout my training, but even now for people to say to me, hey, I know you did that, that project looking at, you know, whatever, duck-billed platypuses or something, and you did that analysis that was really interesting, and they always say really interesting, by the way, that was really interesting, and I have this project that I'm working on, and I think that I want to do that same sort of analysis. So can you tell me how you did it? So, you know, I'm guessing that other people, if I'm assuming most people here are involved in research in one way or another, so I'm guessing if you've been doing research long enough, you've probably had a similar experience. Maybe it's not an analysis, maybe it's like a, you know, an experimental technique, but I'm guessing most people have had that experience. Anyone can be collaborators and competitors, right? You know, you collaborate with someone, you do some analysis as part of the collaboration, and you publish a paper, and then, you know, a couple months later, your collaborator says, oh, you know, like we're starting to do that sort of work in the lab now that we had this great paper. Can you tell us how you did the analysis? And of course, you know, competitors, same thing, right? And collaborators can also be competitors, right? So like you might have a competitor who emails you and says like, oh, I saw your paper, congratulations. Can you tell me a little bit more about how you did that analysis? It can also be like people in totally different areas of research, right? Like maybe I wrote a paper on platypuses, and there's someone who works on, you know, I don't know, redwood trees or something like that, and they want to apply that that analysis method to their own research. Right? So it could be some totally different area of research, but they are interested in how you did your research, and they want to know. And then the most important, I would say, anyone is you in 6 months. Because I can tell you, again, anyone here who's had enough experience, been doing research long enough, has probably had this experience. I've had it many times, where you do some project and you publish it and everything's done. And then 6 months or a year, like usually it's not 6 months, usually it's like a year or 2 years or 5 years later, you have another project that's similar, or you know, someone, maybe that collaborator comes back to you and says, this is, again, personal experience, comes back to you and says, like, hey, we had that like project that we published like 4 years ago. There's a grad student in lab who wants to kind of build on that. Could you rerun the analysis, but like also do this other additional bit? And that would be really helpful for them. And the times where I have done things reproducibly, and I can, you know, I spend more time actually like finding the code, you know, maybe like, still takes like 20 minutes to find the code to run it. But the time when I spend 20 minutes finding the code and like 5 minutes getting it running, and then I come back like the next day or something and look for the results, I'm really happy with me from 6 months ago or a year ago or 5 years ago. That me back then was courteous enough to make sure that me today could redo that analysis without a lot of work. Because there's nothing worse than spending, you know, 5 months doing an analysis, and then you publish it, and then you need to do it again sometime later, and it takes you 4 months to like redo it because you don't remember what you did the first time, right? What I'm not going to cover here is talking about reproducibility in the wet lab. It's important, but it's totally outside of the scope of what I'm talking about here. It's also a lot harder than what I'm talking about here. And there's a lot of, you know, kind of details that are going to be specific to different fields. So I'll mention it here. It is part of the reproducible research process, but I'm not going to talk about it anymore. There's lots of stuff that I'm not going to get into the details of. There are other valid approaches besides what I'm going to tell you today. Like I said, this is sort of my view of reproducible analysis. And other people will have different approaches. I do what works for me, and I'm going to walk through it for you, but you don't have to do things exactly how I do it. And I'm trying to keep this to like 60, 70 minutes, so I'm going to gloss over a lot of details. Some of those details I'll cover when I talk about Git later today, but a lot of details I'm not going to cover today, and maybe at some point, it's not part of the schedule, but you know, maybe some other time I'll cover. The next qualifier that I want to give you is, so my colleagues often refer, and I often refer to this talk as my reproducibility rant. I'm very passionate about reproducible research. And I'm passionate because of things that I've already told you and things that I'll tell you, continue telling you, which is that almost everything that I'm going to talk about today, I have developed approaches based out of personal pain. So like all those times that I didn't do things reproducibly and I hated myself for not doing it. So again, that makes me feel very passionate about it. I might sound a little preachy. I hope I don't sound too preachy, but I want you to understand that my goal isn't to like shame anyone who's not doing things reproducibly. I don't want you to go away from today saying, wow, that's a lot. I can't, you know, I'm doing like one of the like 8 things that he mentions, and like I'm just overwhelmed. I'm gonna go crawl into a hole because I can't do all that stuff. If you leave here today and you're doing like one thing better than you did before, or even, you know, in a month or in 6 months, you say like, oh yeah, I think maybe I'll try that. That's great. You're probably making things better for you in 6 months, and you're also making things better for science in general. So please don't leave here thinking that's too much. It would be great if I could do it, but it's just too much. See what maybe catches your fancy, try it, and then maybe at some point you'll try something else. Not to discourage anyone from like jumping whole hog and doing everything I tell you, but you know, I don't expect anyone to do that. And like I said, this is a process that I've gotten to over years of evolutionarily, you know, adding new tools as I've, you know, had pain in my research. And then the last thing that I'll say is that before I actually started talking more about reproducible analysis, is that reproducible analysis, it's kind of like eating your vegetables. I like vegetables, you know, I often have a salad for lunch or dinner. But, you know, like there's like junk food in the pantry, there's some delicious chips, there's some chocolate chip cookies, and sometimes you say like, oh, that looks delicious, I'm gonna eat that. And usually you know at the time, usually I know at the time, I'm like, if I eat half a bag of chips, I'm gonna feel gross later, but I'm really hungry, so I do it anyway. And so that's kind of how reproducible analysis is. I can't tell you the number of times that I've like sat down to do something. This is gonna take like 10 minutes. I'm just gonna do it really quick. I don't need to like go to the trouble of setting up a Git repo, like no big deal. And then it turns out like that ends up becoming, you know, a more involved analysis. And then later I think like, oh, whoops, I really should have done things reproducibly. So there is a cost to doing things reproducibly. It does add some overhead to the work. It's a little bit more work than just doing something really quick and dirty and being done. But kind of like eating your vegetables, you're less likely to feel gross later on and hate yourself. And I have found, again, through lots of pain and suffering, that it's worth that extra effort to go to the trouble of making things reproducible, because I think it most of the time it really does pay off in the end. Okay, so with all of that prelude, let me talk about how I think about reproducible analysis. And I think I already said this, but like both on Zoom and in people who are here, if you have questions, just interrupt me, that's fine. So I think of reproducible analysis as 3 main pillars. The raw data, the computing environment, and the analysis process. And the sort of like executive summary of everything else I'm going to tell you is kind of built on what my definition was, which is that you need to archive the necessary components of the analysis, each of these components, and you need to archive them in a way that's appropriate for that component, which is really different for each of these components. And that's really the sort of like the goal of reproducible analysis, is to archive each of these things, the raw data, the compute environment, and the analysis process in an appropriate way, and then you have it for later so that you can repeat the analysis. So everything else is like the details. Everything else for the rest of the day is the details of how do you actually archive each of those components in an appropriate way. So I will start with raw data. So when I think of raw data, and I should say, again, some of these things are a little specific for me. Most of the data that I work with is high throughput sequencing data. So usually I'm talking about gigabytes, tens of gigabytes, hundreds of gigabytes, like terabytes of high throughput sequencing data. Sometimes that data is coming from, just like the internet, I'm downloading publicly available data. Sometimes it's coming from the sequencing core here at Duke. Sometimes it's coming from sequencing that students who I work with have actually like generated. And sometimes it's coming from other places like commercial sequencers or collaborators, things like that, other institutions. But ultimately, one way or the other, the data, I have to download the data, right? You'll see later that like almost everything I do is on Duke Compute Cluster. The data is never like spontaneously appearing on Duke Compute Cluster itself. It's got to be moved from wherever it was generated or wherever it was stored to the cluster. So that's what I'm calling download, right? Actually like getting your hands on the data. The next, and so that's just the first step, right? It's sort of like an essential step. It's not necessarily particularly reproducible, or doesn't necessarily need to be reproducible. The next step is thinking about the provenance. And what I mean by provenance is making sure that the data that you're actually computing on now is actually an accurate, correct version of the data, that you haven't lost some of the data in the process, it hasn't somehow gotten corrupted. Some people worry a lot about provenance in terms of intentional tampering with the data. It's not something that I worry about too much. I mean, I trust myself not to tamper with the data. I think that most of the problems with data provenance are not intentional tampering. It's just, so either some sort of data corruption that's unintentional. But we want to be sure that the data that we're working on, so like in my case, sequencing data, I want to be sure that the data that I'm working on is the data as it came off the sequencer, right? And not, oh, whoops, we're missing like 50% of it because the download failed and we didn't notice. Or, whoops, that file is actually, mangled in some way. Usually if a file is mangled in some way, it's not in an expected format, you'll get an error. But there are ways that I'm going to show you of making sure that the data actually matches what it was at a previous point in time. And again, usually you want that previous point in time to be the point in time at which it was actually generated. And then the last sort of component of care and handling of raw data is keeping it safe. So making sure that you do as much as possible to keep it from getting, yes, intentionally modified, but like more importantly, unintentionally modified or deleted or corrupted. Because while I trust myself not to do intentionally modified data, I don't actually trust myself not to do stupid things, because I do stupid things all the time. So mostly I'm protecting myself from me. Sometimes I'm protecting the data from other people who maybe don't know exactly what they're doing. And so that's part of protecting it, is just like setting things up so that if you try and modify the data or delete it, the computer won't let you. And then also having an archive in case things go horribly wrong and the data gets deleted, and those and sort of basic roadblocks to modifying or deleting the data don't keep you safe. So I am going to switch. Oh, whoops! I remember to actually open a window to do this. So I'm going to switch and just sort of like walk through some toy examples of this. I'd actually recommend, so you can later on, I will show you how to within RStudio do this yourself. But for now, is this actually working? How good it is. For now, I'm going to recommend that you just watch and pay attention. And let me find the right file. This one. Let's see, where are we? There, okay. Is this big enough for everyone, both on Zoom and in the room? Anyone might want me to make the font bigger? That one? Okay. Yes, I can make it a little bigger. Good, more? More? Good, keep going? Okay. I mean, you could say a lot more. Okay. Yeah, I guess. Yeah, maybe. Fine, fine. Okay. So I'm going to be showing you a few different chunks of code. I'm not going to go into a lot of detail about what they're doing, but I'll highlight the important parts. So this first chunk of code, it's just making two toy data sets. They're CSV files. I'll show you what they look like in a second. They're very simple. Actually, I'm going to show you what they look like right now. That's what this chunk does. So one of the files is called data1.csv, and it's a CSV file, comma separated value, which means that it's like a spreadsheet, but the columns are indicated with commas. But we only have one column worth of data called the value column, so you don't see any commas. And the values are 1, 2, 3, 4, right? Very simple. The second file is called data2.csv. Same sort of format as the first one, except it's got the values 5, 6, 7, 8, right? All very simple. For what I'm going to show you, it doesn't matter whether it's a 5-line file or 50 gigabytes of sequence data. Everything's going to work the same. It's going to be a little faster, or a lot faster when working with like these simple files. Okay, so I told you about provenance. There are a couple of different ways to deal with that. One is with an algorithm in a program called MD5Sum. I'm not getting at all into the mathematics of it. What you need to understand about MD5Sum and other, MD5Sum is a algorithm that's part of a group of tools or a group of algorithms that are called cryptographic hashes. The idea is that if you feed a file or some text or whatever, it doesn't matter what it is. It can be, an MP3, or it can be a CSV file like this, or it can be sequence data, or it can be a PDF. Doesn't matter what type of file it is. But if you feed a file into MD5Sum, it will generate a what's called a cryptographic hash, but you can also think of it as a fingerprint for the file. And it is nearly impossible with modern computational technology to generate another file that actually has that same fingerprint. So this is used for lots of sort of like complicated, this sort of cryptographic hash tool is used for lots of sort of complicated things in cryptography and encrypted communication, identity verification, stuff like that. We don't care about any of that. We care about the fact that the data1.csv file, running these contents through the MD5Sum program will generate this fingerprint, and we can make another file that has exactly the same content. Doesn't matter what the file name is. If it has exactly the same content, it'll generate the same fingerprint. And there is essentially no way for us to make another file that will generate exactly the same fingerprint. So given those two pieces of information, what we can do is when we initially generate our data, and again, it doesn't matter what it is, sequence data, sound file, whatever, if we run it through this MD5 sum algorithm and we get a fingerprint out and we take a file at some later point in time, or it doesn't have to be later point in time, another file, we can again run it through the MD5 sum algorithm. If it's the identical file, it should generate the same fingerprint. And if it's changed at all, it'll generate a different fingerprint. And so this is our way of telling, we can't tell how a file was changed, but we can tell that it has changed. And I will say that there's like some subtleties here. For a text file like this, there are ways that it could be changed that it looks identical, but actually is different. So like, you can't see spaces here. You can't tell, and I can't tell by looking at it, that whether there's a 3 there, just a 3, or whether it's 3 space, 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 space. But MD5 sum can tell the difference between that, and to MD5 sum looks totally different. Same thing with a Word document, like Microsoft Word document. It could look the same based on the text, but there's a lot of like hidden information, like the font information, and I think there might be like timestamps and history information in that file. So you could have the same text in 2 different Microsoft Word files that would, those files might generate different MD5 sums just because of that hidden information. But, so there are some complications there. But if you have like sort of a simple text file and you have a sort of standard format, and again, you're just like sort of copying files around and you just want to make sure that they were copied correctly, they were transferred, you know, downloaded from a website correctly, things like that, MD5 sum is perfect for that. Okay, so here's our MD5 fingerprint for the data1.csv file. Here's the MD5 fingerprint for the data2.csv file. So I need everyone to memorize those. I'm kidding. You don't need to memorize them. That's what computers are for. So here I just ran, the way I ran MD5 sum, maybe I should explain. Here the program's called MD5 sum, and this is just saying like run it on all the files in the directory, that I'm working in that end in .csv, right? So that's why we got 2 different, we got the fingerprint, MD5 fingerprints for the data1.csv file and for the data2.csv file. And it just sort of, it's right now it's just printing it to the screen. So that's not normally how you would do it. Usually you want to generate those fingerprints and save them to a file. When you're at the point of like, you know, if you're at the sequencing core and you're generating sequence data and you want to do a fingerprint, you would want to generate the fingerprint, save it to a file, and then give it to whoever you're giving the sequence data to. And so that's what I'm going to do here. So this is slightly different. It's saying, again, run this MD5 sum program on all the CSV files in the directory. And then this is just saying, save it to a file that I'm going to call mydata_md5.txt. So with that file, then I can have that file with the fingerprints and keep it with my data. And so later on, I can run the MD5 sum program again with this, what's called a flag, this -c, that says, okay, I have this file that I made before that has the fingerprints in them. I want you to load that file, and I want you to run MD5 sum, the algorithm on the current contents file, and I want you to check and see if it matches up. Does that make sense? About that. So I'll run that right now. And of course, since I just generated the fingerprints and hopefully things haven't been corrupted, it's telling me, yep, that data1.csv file, it matches the fingerprint that was in the mydata_md5sum.txt file, and that data2.csv file is okay too. Right? Everything matches up. So now we're gonna mess with things. So right here, this chunk of text, or this chunk of code right here is going to take that data2.csv file. And if you remember, it was 5, 6, 7, 8. So it's going to put a 3 in the place of the 7. So now it looks like this, 5638. So slightly different file. As far as MD5 sum is concerned, it doesn't matter if it's slightly different or completely different. It's going to generate a completely different cryptographic hash, completely different fingerprint. And so now the data1.csv file, it still matches what's in my the file that I saved with the fingerprint, but the data2.csv file, now the version of the file doesn't match the fingerprint anymore. So it's saying failed, and it's giving me this like big red warning that one of the files didn't match, right? So this is exactly what we want. I mean, like the ideal would be not only could it tell us it didn't match, but it could tell us what was wrong. That's something that's doable, but much more complicated. And takes a lot more data to store. Here, right, it's this little, I think it's 32 characters that have to be saved per file. It's really small. Like I could write this on a piece of paper if I really needed to and check it, or, you know, it's easy to transmit. Questions about any of that so far? Yep.
Are we going to get like the code?
Yep. Yeah, so you can run this. You can run this yourself and play with it later. But yes, we will. By the end of the day, I will show you how you can download into the Duke Compute cluster. And it's actually, you can do it onto your own computer too. All the material that I'm going to go through today, and people are going to be adding it. I don't know who's teaching next week, but whoever teaches next week, I don't know if they've uploaded all their stuff yet, but by next week, it'll be there, and you also be able to download that. But yeah, all the course material will be available to you. Other questions? Anyone on Zoom have questions? Okay. Okay, so that's the provenance part. So the other part that I mentioned is the sort of data protection, which is trying to avoid needing provenance. And so I'm just going to talk right now, or demonstrate right now, how to make files so that it's hard for you or other people to mess them up. So this environment that I'm working in on the Duke Compute cluster, it's a Unix environment. It's going to be slightly different on a Mac or on a PC, but basically all computers have a mechanism similar to what I'm going to show you. Again, this is how you would do it in a Unix environment. So the first thing I'm going to show you, this is the data that I just generated. And we're looking at, these are the data1.csv and data2.csv files. There's the file that has the checksums itself. And then this is the directory that those files are in. So this is what are called the permissions for the files. And there, you'll see that it's a little bit hard to tell here, but you see there are 3 R's there, and right here there's a W. So what these represent is who can look at a file, who can change or delete a file, and then if it's actually like a program, who could actually run that file. You don't really see that here. Actually, for the directory, so the R is for reading or actually being able to view a file. The W is for writing or being able to change the file. And then this last thing here, you don't see it, but for the directory, you see an X. That's for execute. And that's for a directory, it means that you can actually go into that directory or folder. For a file, it means that it's a program that you can run. So none of these are programs, so it doesn't make sense to say that anyone can run them. And then there are actually sort of 3 groups of permissions. So the first group of permissions have to do with whoever owns it, which is me because I made the files. The second set of permissions has to do with people within my group, which my group here, so that's who owns it, that's me. The group is Duke users. And then the third set of permissions is like anyone on the whole computing, on the whole cluster, right? So I can see these files and I can alter them. Anyone in Duke users can see the files, but they can't alter them. So you guys could all see the files. Oh, actually, I don't know if you're on, probably everyone's Duke users. And then anyone on the cluster itself can actually see the files, but can't alter them. So this W here, if this is like important data, I'm worried because again, I don't trust myself. So I can change that with this program that I pronounce as chmod. Other people pronounce it chmod. And so this is going to, here, this is the name of the program. This is a sort of shortcut for the directory itself. So I'm gonna do something to the directory and all the files in it. And what I'm gonna do is, I'm gonna get back to this big R in a second. This is saying for everyone, the A is short for all. The minus is like subtracting. So I'm subtracting the W, which is write permission. So basically, I'm going to make it so that nobody can write to this file. And the -R is just saying like, do it to that directory and all the files with the directory. And then we'll just see how that looks differently in a second. Why is nothing happening? Okay, it's just being slow. Okay, so you can see the difference, right? At the top there was the W. Here, there aren't any W's. So no one can write to this file. Now, I own the file. So if I wanted to change this and make it writable again, I can. So it's not like a super foolproof, like this is not like, you know, a safe in a bank, right? Well, I mean, I guess safe in a bank, and if I'm the only one who knows the combination, then I'm the only one who can get in. But it's not protecting, it's protecting me from being stupid, but not protecting me from being like really stupid or malicious. But we can see what happens if we try and now mess up those files. So the first thing I'm going to do here to try and mess up the files is try and change the contents of the data2 file so that it says this is not the data you were looking for. Right, so this command will, if it works, will overwrite the, what is it, 5638 now. So that's the current contents of the data2 file. And so this would, if this worked, it would overwrite the contents of the file with this is not the data you're looking for. And it shouldn't work because I set it not to be writable. And so as I was hoping, it's going to say permission denied, right? Even though I own the file, I've said, Josh, you are not allowed to change the file. And the computer's not letting me. So I can do the same thing I tried to do again. I can try change a 7 to a 3. Now it's already a 3, so I don't know, it wouldn't work anyway, or it wouldn't do anything, but just trying to change it is going to give me an error message, permission denied. You can't do it. And then if I try and delete it with this command rm, which is how you delete files, actually try and delete the whole directory. Right, so, you know, not necessarily a smart thing to do. It's also going to tell me, maybe? Run. Oh, I don't know why it's being slow. Okay, so it's going to tell me, like, can't delete any of these files. Right? Permission denied to try to delete any of them. So that's, you know, quick overview of like how you can do some provenance, keeping track of provenance of files, and how you can, simple ways that you can keep files somewhat safe. Questions about any of that? I'm just going to run this last chunk here because otherwise later on I have to clean it up. That cleans things up. Any questions? Questions on Zoom? People can think about that while I switch back to my slides.
Okay, I'll ask.
Okay.
I'll ask a question.
Awesome.
With MD5 sums, do those play nicely with like Excel files if you're using an Excel file format?
So you can use it with any file.
Okay.
So the thing that I mentioned about like a Word document holds with an Excel file, that Excel files don't just have the content that you see. There's a lot of hidden information about like fonts, and I think that it keeps some like version information in there. So it's possible that you could have two Excel files that when you open them, they look identical, but actually under the hood, they could be different. But if you have an Excel, and the other thing is that sometimes when you just open an Excel file or like change like preferences for printing or things like that, that will alter the file. So just opening the file in Excel can alter the file. So it is possible that you could have an Excel file that you thought was identical to like another version, but it's not, even though it looks the same. But if you have an Excel file, you download it, you have like the have it set to read only, and you generate a MD5 sum, and you transfer it to another computer, send it to someone else, whatever. You do an MD5, run an MD5 sum on it, and you haven't altered it, it should generate the same MD5 sum. And when I say altered it, like meaning even possibly opening the file with it not being read only.
The observer effect with Excel files.
Yeah,
by looking at it, you change it.
Yeah, which is an unfortunate problem with. I mean, there's some benefits and some drawbacks, but it can be a problem with Excel files that you can actually change them without realizing you're changing them just by altering it and like, say, changing like the print settings or something. Other questions? Okay. So we just went through all this, so I don't need to do it here. Okay. So then the last little bit that I'll tell you about data, I'm spending a lot of time talking about data, but data is pretty important, is archiving as soon as possible. That's one thing I didn't show you. So there are lots of different ways to archive data. One of my favorites is actually to do it for free, which if you're working with certain types of biological data, the National Institutes of Health will allow you to archive your data with them for free. There are several different mechanisms for archiving different types of data with the National Institutes of Health. One is GEO, which is short for the Gene Expression Omnibus. They take, and I have in quotes here, gene expression data, because basically they take microarray data, which almost no one generates anymore, but there's still a lot that has been archived in the past. They take RNA-seq data, and even though it's not actually expression data, they take ChIP-seq data. I don't know why. That's what they do. And they don't take any other types of data. There's the Sequence Read Archive, also run by NIH, abbreviated SRA, that takes almost any other type of sequence data besides RNA-seq data and ChIP-seq data. And I will say, actually, in reality, when you archive RNA-seq data or ChIP-seq data with a GEO, the sequences themselves actually end up in Sequence Read Archive. But you are not supposed to submit it directly to the Sequence Read Archive if it's RNA-seq or ChIP-seq data. You're supposed to submit it through GEO, and then GEO kind of holds part of that information, deposits the sequence data in SRA. I say almost all of those sequence data because if you have sequence data that is protected human sequence data, then it is supposed to go, if you're depositing it at NIH, it's supposed to go in another database called dbGaP, which stands for Database of Genotypes and Phenotypes. So almost always, if there is data that is collected from human subjects, sequence data that is collected from human subjects, it almost always has to go in dbGaP. There are ways that you don't have to do that. If people care, I can tell you. But in general, if it's human sequence data, it should go in dbGaP. There is another database called import, which is an abbreviation kind of for the Immunology Database and Analysis Portal. And they take immunology data, but again, like Geo, if you deposit sequence data and import, the sequence data is, actually I think you're supposed to deposit the sequence data in SRA or Geo and then link to it from import. But like lots of different immunology specific data plus some other data types can go in import. If you're working with data that's none of these, then, I'm getting ahead of myself. I'll get back to that in a second. So if you're working with data that's none of these, I'll give you an answer that's not very satisfying in a minute. I keep telling people to do this, although this is, of all the things I can tell you, this is the one thing that I have not actually gotten around to doing myself, but I keep beating myself over the head for it, which is the best day to be archiving your data at any of these places is the first day you get the data. It is like totally not fun. You get your shiny new data and you want to analyze it. And the last thing you want to do is spend time archiving it in one of these places. But I'm going to tell you, that's the best day to do it, because the worst day to do it is you submit your paper, it's accepted, the journal won't publish it until you've given them the accession numbers for your data that you've submitted to the SRA. And now it's like 3 years since you generated the data, because like it took you that long to analyze it and write the paper and get it accepted and stuff like that. And now 3 years later, you're like, how did I get this sequence? I know I sent it to the sequencing core. Which machine did they do it on? Was it a Illumina HiSeq, or was it a NovaSeq, or was it a NovaSeq Plus? And how was the library made? So again, personal experience, sometimes not my fault, but it is really hard 3 years down the line to remember exactly everything that went into generating that data. And that's not only what the information that they want you to submit along with the sequence data, but that's information that's sometimes necessary for other people to make use of it, which is these databases are there so that other people can use it. I mean, it's there in part for reproducibility, but the idea is that other people might actually be able to extract some value out of data that you generated for your own purposes. So I recommend that people deposit their data as soon as they get it, because it gives you a free backup. And I can almost certainly guarantee you the people who are in charge of doing backup for SRA probably know a lot more about how to back up data securely and accurately than you do. I know that they know more than I do. It means that you have to collect that metadata, all that information about how it was sequenced, like which sample was what. You have to collect it and organize it in order to submit it. And again, better to do that the first day you get your data than 3 years later. And the last thing I'll say is that so Geo and SRA, you can embargo data when you submit it. So you can say, here's my data. I don't want it to be publicly available for 5 years. Or, I mean, you can pick any number 5 or less years, down to like the day. You can say like, what's today, October 20th, 21st. So you could say, if you are submitting data today, you could say, I don't want it available until October, I don't know if you could do 20th or 21st if you were doing it today, but let's say October 20th, 2029. And the nice thing is that you can update that embargo. So like you could log on December 1st of this year and say like, oh yeah, I want to push that embargo forward. So I want it to be November 30th, 2029 now. And you just, in theory, just keep doing that until you actually publish on the data, then they release it, even if you don't tell them to. Well, usually they release it even if you don't tell them to, because that's kind of the bargain that you make. Just in case you don't know, most journals will require you to make your data publicly available before you can publish on it. So you're going to have to do it at some point. You might as well do it when you get the data. So alternatives to NIH are the European Nucleotide Archive and the DNA Database of Japan, which are part of the International Nucleotide Sequence Database collaboration, as is NIH. So you can deposit your data in these places, but they actually end up kind of getting copied to, like if you deposit it in ENA, it gets copied to NIH and the DNA Database of Japan. So often if you have a federal grant, it has to be deposited in NIH anyway. I have in the past, the ENA interface was a little bit easier. So when I've had like non-NIH funded projects, I have submitted it to ENA, but the NIH like website for depositing data has gotten a little bit better. So I wouldn't necessarily do that today. And for other data types, I don't necessarily have a good answer. It really depends on, like I said, I mostly work with sequence data. For some other data types, there are public databases that you can put it in, but it's really something that's specific to your field, and I'd recommend people, if you work in some field where you generate other types of data, look and see what people do in the publications that you're reading, like where are they depositing the data. Questions in the room or on Zoom? If not, I think it is 2:06, so maybe we'll take let's just say take a break till 2:15, so 9-minute break. So let me talk about reproducibility for computing environments, and then we will get to the last bit, and then we'll do some hands-on stuff. Okay, so reproducibility for computing environments. So actually, before I do that, back up, right? I'll just say that the motivation for thinking about the computing environment is something that I think has become less common. Certainly when I was in grad school, it was a huge issue where you'd take a file that was made like a Word file or a PowerPoint file that was made on a Mac, and you send it to someone on a PC who had a PC, or you were giving a presentation on a Mac and you made the PowerPoint presentation on PC, and things just wouldn't work. I don't know, does anyone have that experience where you have yeah, so it still happens sometimes. It used to be way worse. And so that problem of different versions of software not working exactly the same it also happens in data analysis software. So not just data analysis software, but also programming languages, different versions of programming languages, different versions of packages. And so as you might remember, I said that the goal of reproducible analysis is to take the same data, computing environment, and analysis pipeline and rerun the data and get exactly the same results. Well, if the computing environment is, even one package, or is a slightly different version, or like the programming language is a slightly different version, you can get different results. And then it becomes a question of, well, did I get different results because I have like this different version of this program, or did I get different results because there's something wrong with the, like I don't actually have the right data, the data got corrupted, the analysis pipeline is actually different than what I thought it was. And so if you can't get exactly the same results, it's hard to know why you didn't. And so it's important to have a reproducible computing environment. And this is more challenging than you might think, or maybe, I don't know, maybe you think it's challenging, I don't know. It certainly, it took me a long time to get to a point where I felt happy about having a reproducible computing environment. And the approach that I've settled on is an approach called containerization. So what containerization gives you is it gives you the ability to have actually multiple versions of computing environments. It gives you some amount of portability. Depending on, I'm going to explain what I mean by containerization in a second, but I want to sell it a little bit first. So depending on like what sort of containerization system you're using, some actually let you run the same computing environment on a Linux computer or a Mac or a Windows computer. Some are, to do that, it's a little bit more complicated. But it does give you some portability. It gives you definitely portability in terms of like a sort of scalability, the ability to run on a laptop or run on a server or run on a cluster or run it in the cloud, like on Azure or AWS. And all of the containerization systems that I'm going to mention also give you the ability to share the computing environments. So again, share it with you 6 months later, share it with lab mates, share it with collaborators and competitors. And so it takes this sort of issue of like different versions of software and simplifies it, because you can sort of, there's this tool that allows you to make a reproducible computing environment. So I think my next slides are, not helpful. So I'm going to try and really kind of quickly give you a little bit of an intuition for what containerization means. If you've ever heard of a virtual machine, containerization is sort of similar to that in a lot of ways. The like details about how they work is actually fairly different. But like the user experience of a container is very similar to the user experience of a virtual machine. If you don't know what a virtual machine is, that's fine. I'll give you my little story about how I like to think about it. So imagine I have like, say, 3 or 4 different projects that I'm working on. And so let's say this morning I was working on my duck-billed platypus genome project. So in the sort of containerization world, I might have a laptop just for my duck-billed platypus genome project. And so I was going to work on that this morning. So I took that laptop off the shelf and I put it on my desk and I was working on it. And I have all the software that I need for the duck-billed platypus project installed on that laptop. And then let's say like this afternoon, if I weren't here, I'd be working on my, like, I don't know, ant transcriptomics project. Ant, like the little insect, not like my mother's sister. So I take my, although I could do that project too, that's a different project. So I take my duck-billed platypus project laptop and I put it back on the shelf, and I get my ant transcriptomics project computer off the shelf and I put it on my desk and I start working on that. And that has all the software that I need for my ANT transcriptomics project, right? And so when I switch projects, I'm just going to switch laptops. And like even better than that, so like if I, you know, let's say I'm using R version 4.2 for my ANT transcriptomics project. The duckbill platypus project I started like 3 years ago. So like at that point, the current version of R was 3.4. So I got R 3.4 on that laptop. It doesn't matter that I've got different versions of R, different projects. Like for each of those projects, I have the version of R that I need. I have the version of like whatever other tools that I need, and they don't have to be at all related because different laptops. So I don't have to worry at all about conflicts between different versions of different software between those different projects. And so even better than that, I've got this fancy schmancy computer replicating tool so that when my collaborator calls me up and says like, hey, you know, we published that research like a couple of years ago on, I don't know, lizard genomes or something. And so like, could you share with me your computing pipeline for that? Because we're doing a similar project in my lab now, and it'd be great to have that software. So I can take my lizard genomics laptop off the shelf, and I can put it in my magic replicating machine, and I can replicate it and just instantaneously teleport that replicated computer to my colleague, and then they have it. And even better, like people can just like go on some website and like download a laptop with that software installed in it. So they can reproduce anything that I've published, you know, where I've actually made that computing environment available. So that's kind of what containerization gets you. You don't get a free laptop, but everything else you get. And so it's using basically a software definition of a computing environment. So you can have a file on a computer that you can share that has all the software installed in it. And when you're running within that containerized environment is as if you're, you know, you're running on that laptop. Or like another way that I've explained it is, that maybe is helpful, is kind of like Pokemon Go, where you have your phone and you know, you're using the camera on your phone, so it looks like the real world on your phone, because it basically is, but there's like this animated character imposed on the real world. So it's kind of like that in some way, that you have this environment that can like make it appear as if you have certain software available to you within that environment, like a Pokemon character. It's a little bit, I will say that containerization is a little bit hard to wrap your head around, and I'm not going to go into too much more detail about. If people have questions about it, I'm happy to talk like during the break or afterwards. I will tell you just that a little bit more about containerization. There are several different platforms for containerization. Docker is really the original. What I actually use a lot more of now is something called Apptainer. It used to be called Singularity. There's another platform called Podman. There are others, but those are kind of the major ones. What I use mostly on compute clusters is Apptainer. And I'm not going to really explain why right now, because I don't want to get into it. Questions about reproducible computing environments before I keep going? I will just tell you that if you were here last week for the not last week, 2 weeks ago, for the like introduction to our session, and you're here today, you will be working in a containerized computing environment, even though you won't know it. Well, you'll know it because I just told you. But the environment that we use for the whole workshop is a containerized environment. And one of the big advantages is that it means that everyone kind of has all the same software available, all the same version, everything's the same. Any questions about containerization before I keep going? Questions on Zoom? Questions in real life? Okay. So let's talk about that, the third pillar, which is having a reproducible analysis process. So when I was talking before about containers and software, I didn't really define that too well, but usually what I mean by that is like existing software that you're downloading from somewhere. So like it can be R, it can be like a software package like BWA, if that means anything to you. It can be like the software, like if you're working with single cell data, it can be Cell Ranger. When I talk about the analysis process, I mean code scripts that you are writing as you're doing the analysis or as part of the analysis. So there can be a little bit of a subtle distinction there, but hopefully that makes sense to everyone. My sort of like big level bullet points for having a reproducible analysis process is to script everything, to share everything, and to use version control. And I will explain what I mean by each of those now. So when I say script everything, I mean that really, ideally, you should be using any sort of programming language or environment that allows you to essentially write code in one way or another. So that can be R, it can be Python, it can be shell scripts, it can be R Markdown, you can make files, Jupyter. There are lots of other options. What I really encourage people to try and avoid as much as possible is, well, I have here Excel, but also there are other graphical environments that can be tricky to reproduce. I like to pick on Excel. Not that I never use Excel. I mean, I use Excel for some things, but I don't use Excel for data analysis. Like making a table to like keep track of the dates and the different topics of the workshops. I'll do that in Excel. Making figures or analyzing data, I don't, because Excel has lots of problems. One of the big problems is that Excel mixes data and code. So it can be really easy to mess up the data. I guess I haven't shown you where, so I have notes from that sort of note version of these slides, or I will make that available to you and I'll show you before the end of the day where to find it. If you click on the links here, several different stories about places where Excel has created problems. The one that's like my favorite is this set of 4 links here. Rogoff and Reinhardt are famous economists. I can't remember if either of them has actually won a Nobel Prize. I feel like one of them maybe. I don't know. Anyway, they're famous economists. They published maybe 15 or 20 years ago research on like how different countries should, or how countries should make decisions about like economic problems. And so that, I think it was really one big publication that they had that was used as the basis for world governments and countries across the world making decisions about how to handle the financial crisis in 2008, which maybe some of you don't remember. And so countries made decisions based on that research. And it turns out that some grad student who was like taking a course where they had to like go find some published data and like reanalyze it, reanalyze their data, Rogoff and Reinhardt's data, and found that they'd made Excel spreadsheet errors. And that when you correct that, like they'd like shifted a column or something. I don't remember exactly what it was. When you correct that, like decisions that those countries had made in 2008 about how to respond to the recession like maybe they should have made different decisions. So like no work that I have ever done and probably ever will do is going to affect the decision making of economies in countries around the world. This is kind of a big oops. And really, like, anytime you're analyzing data, if you're using Excel, you're at risk that you're going to make an oops. Maybe not quite this big, but that could actually alter your results. So lots of fun stories. So Excel has problems. It is not to say that if you script things, you don't have mistakes, but the problem with Excel is that it can make it hard or impossible to actually find the mistakes unless you do like very careful sleuthing. Whereas if you like write code and you add instead of divide, or you load the wrong column, it's much easier to go back and look and see like, okay, what is this doing? Whereas, you know, Excel, if you shift a column or, you know, you move some values around, delete a row accidentally, or, you know, like you delete like one cell and so everything gets shifted up, it's actually much harder to find that problem. Okay, so that's script everything. Share everything, meaning that, again, this is for reproducibility by you or by other people. Your scripts that you're actually writing to do the analysis, sometimes there are like parameters in like how you ran a function or ran a program that like you need to keep track of, and so there are different ways to keep track of it. But if you like embed those in the scripts, that's one way of keeping track of it. There's almost always metadata that goes with the data. So like, again, I work mostly with sequence data. So when I think about metadata, usually I'm thinking about, okay, here's a sequence file. What is it like? Where was the sample collected? What date was it collected? Or like, if this is from a mouse, was it a wild type mouse or was it a mutant mouse? Was it, did that mouse get the control? Like, was it a negative control, so it didn't get a treatment, or did it get treatment A or treatment B? Was it replicate 1 for the wild type mouse getting treatment C, or was it replicate 2? That's what I think of as metadata. So like, if I just have a sequence file and I don't know which mouse it came from, then that data is useless to me, right? So you almost always need some sort of metadata to tell you like how do you make sense of the actual data that you collected. And in order for the analysis to be reproducible, you have to share that metadata. Usually for things to be reproducible, you need some sort of documentation. Like what I really like to do is have, well, so sometimes you might have like the sort of code that you wrote to do the analysis, the scripts, maybe you have 10 different scripts, and they have to be run in a certain order, right? So the documentation might say, okay, run this script, then run script number 7, and then run script number 5, run the script that says like, you know, this script takes a really long time to run next. That's one way to document it. I like to actually have like a sort of superscript that it's like runs everything. That's a little bit more work to get that running perfectly, but then like my documentation is like run the superscript and come back in 2 days and it'll be done. And then the last thing that's kind of optional but nice is that actually you can, with some of the things that I mentioned before, like R Markdown files or Jupyter, particularly R Markdown files, but also Jupyter, you can actually take those documents and render them into an HTML file or a PDF or a Word document that has the text and the results and the images all embedded in it. And that's really nice because you have the code mixed with the text. And it's particularly useful for situations where, again, I've encountered this many times, where like, you know, you have the first version of the manuscript and you say like, oh, you know what, I like here, I set the filter cutoff at like 10%, but I think it makes more sense to put it at 5%. So let me rerun things. And then like, so now you have a new figure, or maybe you have a different p-value, and then you gotta go like update it in the Word document, and you know, you gotta update the figure, and then you gotta update the like, you know, the number of animals that has significant value. If you write your manuscript as R Markdown and you have the figures auto-generated from code that's in that R Markdown document, and you like, when you say like the number of animals that had significant results, you can actually embed that as code in the text. So it gets automatically updated when you rerun that R Markdown document. So that's like an ideal. It can be tricky to do because most people have collaborators who don't know what R is or don't know what R Markdown is, but you can, at least as a first pass, do that. Sometimes I can get away with it. Sometimes I'm working with collaborators who are like, this is a new Word document. You can also, you know, even, like I said, you can actually take an R Markdown document and render a Word file from it. So at least for that sort of like first pass before you share it with the collaborators, you can do it in R Markdown, and then you can generate a Word file from it with at least that first draft, and then send that Word document to the collaborators. I'm not going to get into that, but I just want you to be aware that that is an option. Okay, we're going to talk about version control now. And so I have oh wait, don't do it. Sorry. I need to switch the poll. Don't do anything. Let's see, how do I do this? Okay, now try it. And it should say, what do you know about version control? It's actually working. There was that little like padlock on it, and I thought, it probably just means that I haven't activated it yet. Okay, I'm not sure. Well, let me look here. Activate it. Wait. Oh, there's a little padlock that I can click on. Okay, try it now. I don't really know what that means. I don't know how I locked it. Oh, I can see where it's telling me. Got 10 responses. Okay, things are slowing down. Any last minute responses before we okay, so what do people know about version control? Make this bigger. No one uses version control for everything. I'm almost everyone's heard of it. Good. Heard of it, but don't really know what it is. I know what it is, but don't really use it. And it's most people, and I use version control sometimes. Okay, cool, that's helpful. So I'm going to, hopefully, in the next, say, 10 or 15 minutes, you'll have a better idea what version control is. And hopefully by the end of the day, you'll feel kind of comfortable using it. Okay, so this is one way to think of version control is another thing that I find really hard to describe. So here's one way to think of it. Has anyone ever had this experience? I'm probably the only one, right? No one else, right? So I will suggest to you that the problem here is something that I learned when I took a computer science class in college. The professor said to us, you should do what humans can do well and let the computer do what computers can do well. Now, at that point in time, computers were less able to do things like write, a book, which they can do now. Well, is we can debate, right? But things like this, keeping track of like different versions of files, we are not good at that as humans. Or I speak for myself as a human, I am not good at it. Maybe some other people are. Computers are very good at doing this sort of thing. And so this is one thing that version control handles really well. I will say that this looks like it's probably a Microsoft Word document. You can use version control. The version control system, Git, that I'm going to be talking about mostly a little bit later, you can use it on Word documents, but you lose some of the benefits when you're working with, you can use it for any type of file, but Git and a lot of version control systems actually are at their best when working with text files, so they're really designed for working with code. So you lose some of the benefits. It doesn't mean that you lose all of them, but you do lose some of the benefits. So this is, a little bit less relevant, this like Word document that that's getting passed around, but still true. So one way that I like to think about version control is it lets you do all these things. It lets you keep track of changes that you've made. It lets you sort of back up or rewind to like an older version of the document. It lets you do what's called branching, which means that one way I think about it is like, oh, okay, I did this analysis. This is great. I think I want to try doing it like this slightly different way, but I have something working right now. I'm not sure if this other thing's going to work. So I don't want to lose what I have. So I'm going to do a branch, which means I'm going to go off on a separate path, but I'm not going to mess up what I have. And if the separate path actually ends up working out, then I can remerge that branch with like my main path. And if it doesn't work out, I can just like throw it away. And I can just switch over to the original branch that I have. It also makes collaborating on projects really easy, or as easy as it gets, and it makes it so that you can publish the software for the project also sort of automatically, close to automatically. We will, like I said, hopefully you'll have a little bit of a better understanding once we actually do some hands-on activities. I will just to give you like a little bit of a taste. So this presentation that you've been seeing all of today is actually, I made in R Markdown, and then I knitted it, like rendered it using one of the options for R Markdown, which is called IO slides. So this is showing you like an earlier version of this R Markdown document. So what the version control is doing here is green is a change that I've made, or a change that I made at one point in time. And then red is the old version of that line. So you can see that like at one point I had a line that said archiving raw sequence data alternatives. And then I changed that to alternatives to NCBI. And now actually it's been changed again. I think like alternatives to NIH, maybe, I don't remember. So this is one thing you can do, is like you can compare different versions. You can compare the current version to the last version really easily. You can compare the current version to like 23 versions ago. It's slightly harder, but not actually that much harder. So that's just one simple thing that you can do. And just to like give you an idea, I mentioned before that like you lose a little bit of the power with like things that aren't text documents. So like like I mentioned before, Word, like Microsoft Word file, there's a bunch of other stuff in there. So like a lot of, if you actually open the file and look at it as text, a lot of what you'll see is like, looks like gibberish because it's got like the font information and the like undo information and stuff like that. So if you can do version control on a Word document, but like the changes might be like one type of gibberish to another type of gibberish, and so it doesn't always, that won't necessarily make sense. So that's one of the things you like. It's not quite as much of a benefit for a Microsoft Word document. Yep.
Sorry, maybe I missed it. Is this version control like in a Word document, or is it also in a...
So this is specifically using a version control system called Git that I'm going to be introducing to you later. Yeah, so Word actually does have some sort of version control. It is not as powerful as this, and people probably experience it can be like kind of weird and a hassle. I mean, maybe Git can be weird and a hassle too, but in different ways. So yeah, so this is a sort of general, it's an open source version control system, and we're gonna, like I said, we're gonna like use it a little bit later today. Other questions on Zoom or in person? Okay. So I already mentioned Git, so that's one type of version control software. It is, I would say at this point in time, by far the most popular version control software. The probably second runner-up is something called Mercurial, which is not very popular at all these days. And then there are other things. There are older versions of version control software that I'm not going to bother mentioning because there's no reason why you should use them. And then I'll just mention, but we're kind of like going to experience this a little bit later. There are what are called remote repositories, hosts that you might have heard of, GitHub, maybe you've heard of Bitbucket, probably not. GitLab, and Duke has an instance of GitLab. We'll get a little bit of a feel for how you use these later. So for some of those features that I meant, you actually don't need these remote repositories, these public remote repositories to use Git. But if you want the features of like collaboration and publishing, then that's when these come in. Yes, my demo. So you remember, I'm almost done. I hope I'm almost done because I want to have some time to talk about Git. You should remember, hopefully, at the beginning, I did something in this terminal. Where'd it go? And I told you that I was going to explain later. So what I did was a demo. Actually, instead of talking, I should be finding it. Where did it? Our studio, there it is. Okay. So what I did was start running a reproducible demo. The code to do that, you saw me just like copy and paste it. It was like 4 lines of code, I think, 5 lines. A few of them were like not strictly necessary. But basically it started an analysis that I set up to be totally reproducible. It's actually a little bit of a microbiome analysis. The details of what it is aren't so important. The fact that I think is fun is that with those 4 or 5 lines of code, I reran an analysis that probably took me, I don't know, a good week or 2, maybe longer to actually set up. And to rerun it, it took me, you saw, like maybe 30 seconds. I mean, it took the computer 15 or 20 minutes, but my time, it took 30 seconds, right? And I don't really care about the computer's time as long as it's, you know, within the order of like a week or a couple of weeks. And so I'll just show you a few of the output files just so that you can be like, wow, that's amazing. So here's with like pretty pictures. So here's one of them, like, look, pretty picture. So all of this was, you know, rerun, like I said, with 30 seconds of hands-on time. Lots of pretty pictures there. I'll find one more and then this is a good one. And the point is, like, this is really like my sort of gold standard for reproducibility. I don't always get here where, you know, it is a fair amount of work to get it to the point where you can, you know, have 2, 3, 4 lines to run stuff. But what those 4 lines did is downloaded a script that then when I ran that script here, and should be showing you pretty pictures while I talk. Then when I ran that script, and that script itself, it downloaded the data, it downloaded the computing environment, and then it downloaded the rest of the analysis code that then generated these reports with these pretty figures by running the analysis code in that computing environment on that data that was downloaded. So it's doable. And I'm not saying it's easy. It is work, but it's not like 10 times as much work. It's like, you know, maybe an extra 10, 20%. And the you in 6 months is gonna be really happy that you did it this way. Okay, so that's the reproducibility demo. What else do I have to say? I think not much. Yeah, I'll talk really quickly about organization. Again, this is my strategy. I like to have the raw data in like one directory, the output from the analysis in a different directory, like not the same directory as the raw data, and then the code, which I'm always going to want it to be in as a Git repository in a third directory. I think it's pretty common. I think I probably did this early on to like mix 2 or 3 of those things. And that is dangerous. It's mostly dangerous because you risk accidentally overwriting things. You can accidentally overwrite your raw data. You can accidentally overwrite your code. I almost never care about the output directory because I consider that totally disposable. Because even if it takes me a week to rerun the analysis, it doesn't take me a week. It takes the computer a week to rerun the analysis. So I will often actually, at the end of you know, at places in the middle of a extended project, delete all the output and rerun everything, because it's not uncommon to, like, when you're going along and you like generate, you know, you run your analysis, you're not starting always from the beginning, you're starting from like some intermediate step, and it turns out, oops, I changed something that resulted in like one of those intermediate files being different, but then I didn't rerun it, and so now when I rerun everything, things don't work out. There are going to be exceptions, right? I have the advantage that I mostly work with microbial data, so if it takes a week to run an analysis, sometimes it does, but that's usually sort of at the longer end. Whereas, you know, some projects with, say, human data, they might take a couple of weeks to run on, even on a cluster like Hadoop compute cluster, right? So there's, you know, if it was going to take me a month to rerun stuff, maybe I'd be a little bit less likely to do it. But I'm usually happy to just delete that output directory and rerun stuff. But of course, to delete that output directory without deleting raw data, I got to have it in a separate place. So this, again, this is my organizational strategy. There are actually lots of other ways to do it that are more detailed than this. And I will point you to, again, I'll point you to the notes in a second, but here's other descriptions of how, other ways that you can organize projects. And then the last thing I'll say is I have links to a bunch of different files. This, like, why should I use version control, and like some of the other ones probably do a better job of explaining version control and why you should use it than I did. So feel free to read those in your spare time. There there are a couple of, at this point, like kind of old articles, good enough practices in scientific computing and best practices in scientific computing that cover some of the stuff that I talked about. I'm pretty sure I don't do best practices. I'm not sure if I do even good enough practices, but I do okay practices. And I think that's it for now. Actually, maybe really quick, I'll just show you, so you know where to find them. If I can find it. Okay, so here is, so this is what I showed you at the beginning, the material for the workshop series. If you want to find these notes that I just went through, I'm going to leave this here, but if you click on the, no, not the schedule, this data science workshops link, I'm gonna actually add links within the schedule here just to make it a little bit easier to find. But I haven't done that yet. So if you go into lectures, come on, there we go. And then this is, it's a little hard to see. I think, actually you can do either one of these, but this, so organized to make it a little bit easier, the files are numbered here. So 01 is if you were here 2 weeks ago, that's the files. 02 is the second file for the whole series, which is what I just went through. 03 we're going to cover after we take a break. So the sort of notes version of all of that is here. All of everything that I just went through, including those links that I just showed you. Questions from in the room or Zoom? Or is everyone ready for a break? Okay, if there are no questions, let's aim for let's aim for a 5-ish minute break. Let's aim to get back at 3:05. If you can open RStudio on Duke Compute Cluster, or just log on to Duke Compute Cluster during the break, that'd be great. I'll go through it, but like, you know.
What did you say?
If you can log on to Duke Compute Cluster, and actually I will put the link right. That's the link that, so the easiest way to get there, actually, as far as I'm concerned, is from here. So if you go to this page down here, there's DCC on demand URL, and it does not seem to be valid anymore. Okay, I'll try and fix that. One of the links I showed is not valid. I mean, for my slide. But here, if you click on this DCC on demand URL, that should get you, it'll get you to, you need to put in your net ID and password. Mine's being really slow, but okay. And aim for 3:05. I'm gonna go get some water. Actually, I'm gonna set things up. If you don't get there, it's fine. I'll walk through.
Yeah. Just let us know.
I gotta make this smaller.
Yeah, clusters, right?
Don't worry about, just if you can get to where it looks like this, you're good. And actually, I want to close. Where did my other window go? Let's close this. Oh no, I didn't want to do that. That's to tell my joke that I was going to steal from someone else, which is, it's a beautiful day outside. Why are we here? In a windowless basement classroom. Anyway, the sacrifices we make for reproducibility. Okay, so now we're going to do like a walkthrough. Yeah, I'll try standing up. We'll do a walkthrough of just like introduction to kind of get a feel for how to actually use it. I am going to, what do I want to do first? So I'm going to be working through, if I can find it. So I'm going to be using my own notes, because if I don't, then I'll mess up. So I'll show you the notes I'm going to be using, but I'm not going to actually show them. You don't need to use the notes, because you should just follow me. But if you want to like have them for later, or if like, you know, I would say, I'm not going to say if I go too fast, because if I go too fast, tell me to slow down or ask me questions. Because if you miss something and you're like, oh, I'll just figure out myself in a second, you're just going to get more lost. So I'd rather you stop me. And but you will have these if you want to go through again later. So it's in here, the same directory. I said I was going to show you where it was. Now what am I doing? So if you're at the main page, oh, actually, I'll just say, if you don't already have this open, then here's the link, DCC on demand URL from the main page. But if you want to see the notes, you go to the data science workshops and then lectures, and you can see the path right here. And then file 03, which is day 2 get overview.md. These are the notes I'm going to be working from. And now I'm going to take this window and I'm going to put it here so that I have them for notes. And then over here, is anyone not on this page? Yell now, because I'm going to keep going if you're not, if no one yells. Okay, so then what I want you to do is click on, let's do this. So if you open the window, you can click on this little thingy that's the last little, I don't even know what that shape's supposed to be. Some of you, maybe if your window's open like wide, they'll say something else, which I don't remember what it says because I can't get it wide enough here. But it's this last thing here. And now it's gonna take some time loading. Oh, come on. Really? Okay, we're going to go with plan B, which is if you click on this interactive apps thing, it looks the same pretty much as what you'd see if you click here. Oh, there it goes. I'm just being impatient. Okay, so on the side here, you're going to see several different interactive apps. You want the top one, which is the CHSI RStudio Workshop. So if you click on that, you should get here. No one needs to change any of these things. There's the possibility that you'll have something else. Some people might have something else showing up under account than what you should. And I'm one of those people because you want HIV R25 2024 showing up there. So if you have something else showing up there, you should click on the arrow button and select HIV R25 2024. If it automatically said that, just leave it. And then the other thing is that some people might have something besides CHSI high showing up here. If you do, then click on this and select CHSI high. Anyone need me to go through that again? Everyone okay on Zoom? I'll assume that silence means yes. Okay, and then once you're all set with that, you can click on the blue launch button, which I'm going to do now. It will, it's being a little laggy. It should take you to a new page. Which hopefully you are all getting to faster than I am. What this is going to do is going to open up an RStudio session running on the cluster. So this, oh, that's not a good sign. Is everyone else getting that?
I got the
RStudio?
yeah, RStudio.
Just me. It could be my computer, which might be annoying if it is. Come on. Okay, let me just do nope, that's working. Well, at least it's me that's having the problem. Okay, so what this is going to do is it's going to start an RStudio session running on the cluster. So there are kind of two main ways to use the Duke Compute cluster. One is through a system called Open on Demand. Really, I don't know what. I might have to resort to using another web browser. So there are kind of two main ways to use Duke Compute Cluster. One is through the system called Open on Demand that lets you use RStudio, Jupyter. On DCC, we have Visual Studio Code, and we have like a sort of a Unix like desktop. Oh, there. Wait, nope. Okay, come on. Quit fiddling around. There. Oh, there we go. Okay. Yeah. So it'll look like, it should look like this, and then eventually you'll see here it says queued, and then sometimes it'll say like running, and then I think it says running. Oh no, it says starting. I don't know. There are three different things it can say. So then eventually it should get to the running. And then, is anyone not here? Or am I the slow person? Okay. Then you should click on this blue button here that says connect to RStudio server. Oh wait, I have to set myself. Richard, are you gonna yell at me when I need to shut up?
Yeah, I can.
Cool. Well, I'll set a timer just to remind me. So you don't have to like strain your vocal cords. Okay. So now you should have RStudio open. Anyone not have RStudio open on Duke Compute Cluster? Cool. I'm glad that I am the person who's at the back of the line. Uh-oh, now where did my notes go? There we go. No? Yes. Okay. So we're going to do a quick introduction to Git. I already mentioned it before. So why are we using Git as opposed to one of the other version control systems? The main reason I will say is that it is the most popular version control system around. I am not telling you that popular is always correct, is always the best, but there are good reasons why, in the case of Git, being the most popular is useful. If you have a problem with Git and you Google the problem, you're going to find a million answers. It is, so that's like an advantage of being popular. So it is super powerful. So it's actually developed by the people who developed the Linux kernel, so like the main part of the Linux operating system. I know for sure, so that's like a group of like 1,000 people. I know for sure that they're doing more sophisticated things with Git than I will ever need to do. So I know that any feature that I need from Git, like it's already there. So it's really powerful. It's distributed, which means that I can have a local version of my Git repository. I'll explain what that means later, but basically just that project. And then I can replicate it other places. But those like different places that I have it are kind of co-equal, right? One isn't like more important than the other. Back in the old days, like when I was doing my PhD, of version control, you had like a sort of central repository. And at the time, if you weren't connected to the internet and you were, working on your, working on your code and using version control, you couldn't really do anything if you couldn't connect to the version control server. Which, like, I realize you're like, oh, whatever, I can have my phone as a hotspot and I can be like hiking somewhere and doing version control. But back in those days, I know it's hard to believe, but internet was not available actually everywhere on the planet. And so that was actually kind of a hassle. So with distributed version control, it means that that's not an issue. It is free and open source, which is nice. But it's also just good version control software. It is, I will say, there's a steep learning curve. I'm going to try and like make that learning curve a little bit shallow, but it takes some getting used to. Okay. So should I make, is this a good size for our studio or bigger? Anyone want it bigger? Okay. So the first thing that we need to do is do a little bit of setup in our studio because it isn't always set up. Mine, I think, should be, but I don't know what the defaults are for new accounts on DCC, so we might need to set things up. So go under Tools here, and you want to go all the way to the bottom to Global Options. I'm going to go ahead and click on that. And it should be popping up a new window. Anyone not here? Okay. So you need to, where is it? On the side pane here, you want to click on Git/SVN. And at the very top, it says Enable Version Control Interface for RStudio projects. If that checkbox isn't checked, check it. So you should have a little check mark there. And that is the only thing you need to do here. And then you can click on OK. Anyone not ready for me to click on OK? I'm clicking on OK. Okay. So that's the setup that we need to do for now. Okay, so now we're going to open up a new project. And there are a bunch of different ways to do it. For now, I'll go under File and click on New Project. And then we're going to say New Directory, click on New Directory. And then New Project again. And now we're getting to this dialog box. Anyone not here? This is the new project wizard. Okay, so for the directory name, I want you to type planets. And then for the create project as a subdirectory of, you want a tilde there, that means your home directory. If you don't have a tilde there, I'll show you how you can get there. And click on browse, and then it'll open this dialog box here. Click on home. This will look a little different for other people than me because I have a lot of other stuff in my home directory. But if you click on home there, and then click on, and it should then have a tilde up here. And then if you click on choose now, you should have a tilde there. Anyone not have a tilde there? Tilde is that little squiggly character. Okay, and then the last thing you want to do is you want to be sure that the create a Git repository is checked here. And now you can click on create project. And while that's spinning its wheels, which hopefully shouldn't take long, I will just say as a disclaimer that this tutorial, I wrote it for RStudio, but I totally ripped off a tutorial from an organization called Software Carpentry, which they have a really nice Git tutorial. They have a lot of other nice material, but I modified it to be used for RStudio. So I'm responsible for the RStudio part. I'm not going to take credit for like most of the content, which also means that I'm not going to take blame for the corny jokes that are part of this tutorial. You'll see what I mean. I'm just telling you. The content's great, the jokes are terrible. I mean, like not jokes exactly, but you'll see. You'll see what I mean. Okay, and the name planets, you'll see why we're calling it planets in a second. Okay, so the next thing we need to do is, you should see in the upper right, there's this pane here, and there's one of the tabs is called Git. And so you're going to click on that. And when you click on the Git tab, you should see two things here. These are actually two file names, and then next to them there should be question marks in orange squares. So this is our first like interaction with Git. And what the question marks mean is it's Git telling us, hey, I see you got these two files in your directory that you set up as a Git repository, and you haven't told me about those. I'll just, as an aside, I'll mention that RStudio made these two files for us when we made a new project. So we didn't actually do it ourselves, but Git doesn't know any of that. It just knows that there are two files there, and we haven't told it anything about these files. And so those orange boxes with the question marks are Git essentially saying, hey, these files are here. You haven't told me anything about them, so I'm not taking care of them right now. Until you tell me to take care of them, they're your problem, not mine. Question?
Yeah, I don't have those question marks.
What does it say in the, are you on the Git pane?
Yeah.
And you don't have anything? Yeah. Does it say planets in the top right here?
Yeah.
Interesting. Huh?
Like git ignore and everything.
Yeah, if you look in the file dialog box down here.
Yeah, I have them in the files, yeah. But I don't have the H history. I have the Git, first one and the third one.
The .git ignore and the planets.r project. Interesting. I don't. So one thing you can try is this, the circle arrow thing. That's the refresh.
Okay, now I have it.
Okay. Well, interesting. And sometimes it will, but usually when you open, well, as long as it worked. Any other questions? Okay, so we are, for now, we're gonna say like, let's have Git actually take care of these files for us. And so the way you can tell Git that you want it to take care of the files is a two-step process. The first step is clicking on these boxes here under the staged column. And you will see that the orange question mark boxes go away, and now you have an A in a green box. The A is short for added. So adding and staging are synonyms. So this is the first step in the process. The second step in the process is something called committing. So we haven't really yet, when you stage it, it's getting ready to commit. It's getting ready to have Git take care of it. But until you commit, it's still sort of like in this limbo. So now we want to do a commit. And the way you do that is you click on this commit button here. That will open a new dialog box, which is the commit dialog box. And one of the quirks of Git is that you always have to, when you commit things, you always have to have a commit message. And if you've ever done any programming and or took a programming course and you were taught you should have comments in your code, and the comments should be like an explanation of what's going on in the code. Commit messages are kind of like that. The commit message should be sort of an explanation about like what's going on in this commit. And so you'll see in a few minutes why it's useful to think of a commit message. But when you're writing a commit message, you should think of the U in 6 months, because it is not uncommon for me to have a problem. I'll have like some bug show up and I'll think, oh yeah, I had this show up in the other project. Which project was that? Oh yeah, I remember which project. How did I fix it? I don't remember how I fixed it, but I can go look at my Git commits for that project and I can find it. Now, if you actually had to like flip through all the changes that you made, for me, that could be tens of changes across multiple files. But if you have a good commit message where you say, fix bug X with whatever, then that just means reading through a couple of commit messages, reading through maybe like 50 commit messages, which usually you want them to be kind of, at least have a short sort of first line. And so that's what you're aiming the commit message for. So all that said, and your commit message shouldn't be, you can actually see here, I told you that the green tells you what's new. So here, like the file's new. So the whole thing is green. We'll see when we start making little changes that the whole file is in green, right? But you can actually see this by looking back through old commits. We'll see that too. So you don't actually need to like, just like a bad comment, if you have like in programming, like in a program, if you have a line where it's y equals x plus 3, and your comment is add 3 to, what did I say, y equals x plus 3, add 3 to x, that's a terrible comment, not only because it doesn't tell you anything useful, but if you know how to program, if you know how to read that programming language, you can see that. So there's no point in having that comment. So the same thing with the commit message. If the commit message is just like sort of repeating what you could easily see, that's not helpful. It should kind of summarize. Sometimes it's really hard to come up with a good commit message. And we're gonna be wimp out a little bit here and say, for this commit message, we're just gonna say first commit. But it's not like terrible, because really we're just committing these like initial files. So that's okay. But, maybe we could do better, but it's not a bad commit message. So you got to type your commit message and then click on the commit button. And nothing happens. Try that again. Oh boy. Come on. Okay, there. So for me, I'm getting this message here. So this is where like Git is talking back to us. When you do commits, it's like a little bit cryptic. But it's saying nothing to commit. Wait, nothing to commit, working tree. Didn't I? Oh, because I clicked it twice. Yeah, so this is what it said first. When the commit works, it's usually like a little bit cryptic. A lot of the messages that you get from Git are actually really helpful. The commit messages, the commit like sort of feedback it gives is like a little bit cryptic. Did anyone get anything different than this? Did you get something like a error message asking for like email and username sort of thing? No?
No, it said it automatically.
Yeah, okay, so you might get that. Yeah, so it actually, when you do a commit, it records the email address and the username of the person who did the commit. And that's so, I say this only half jokingly, so people know who to blame. It is like, you know, so you know who did it. And like, if there's a problem, like you can go back to them later and be like, why did you do this? So it will, so we can set Git to, so by default, it'll try and like figure out what your username and email is. You will keep getting that message until you set it up for the first time. So why is it being so slow? So one option, you can ignore it, or you can do this, which is to type git config -- global user.email, and then you can put your email address or just make something up. I'm going to put my email address. You should not put my email address. Sometimes people won't put their real email address because when if you put this on a public repository, that's actually, and you make the repository, if you put it on like GitHub and you make the repository public, then your email address becomes publicly visible. So just on the odd chance that it's not in a million spam databases, like they'll get it from GitHub. But so some people won't put the real one in. I'm just gonna put mine in. So git config -- global user.email, and then your email address in quotes. And then for the username, you can do the same thing, almost the same thing. Git config -- global user.name, and then I wouldn't recommend putting in my name. I'm putting in my name. You should put your own name in. Okay. But I think that the commit probably worked. Does it not? Anyone not get that working? This is one of the, like, in general, the RStudio interface kind of does 99% of what you want to do. You can do everything you do with Git from the terminal, but I actually like using the RStudio interface better for most things. Yep. What's the error message? Oh, yeah, it could be that it's the problem that I was having with it being slow. It could be that either there's a network problem. So one thing you can do is just try and reload it. So like on my web browser, it's the like little circle thing. And another thing you can do is go back here to this sort of main GCC on demand thing and click on connect to RStudio server, which now is going to freak things out because it. I'm blaming you. I'm blaming you. Yeah. Okay. Did that help? Usually, is it working now? Yeah, I don't know what's going on. I don't know if it's our network or if sometimes cluster will have like weird stuff going on. Here, I can. This is the. There it is, if you need to do it again. Is that big enough?
I'm not able to write that.
And are you, another thing to check is, are you in the terminal tab?
Yeah.
Okay.
Yeah.
And is it, no, what's going on here? How are people doing on, anyone having a problem on Zoom? Because it could be our network. Ironically, sometimes this building is, the network has issues.
Very slow.
Oh.
Yeah, I think
Put your name. And that's it. And do enter. Actually, maybe, oh man, I'm running way behind schedule.
something's wrong with the server. Yeah.
Is everyone, is it working for everyone now? Anyone not like have it working now? Okay, so I'm gonna keep going. I forgot to give my little explanation of what Git is actually doing, but we'll skip that for now. Okay, so we kind of got things basically initialized. So now we're gonna actually make a file and we're gonna start making edits to it. So if you wanna go to File, New File, and we want a text file, which is all the way down here. Anyone not have, and so that should open a new pane here, a source code pane. Anyone not have that? So go to File, New File, and then down here is text file. I have two of them. I only need one. Anyone not have that? It should say Untitled 1 there. Okay. So now things get kind of silly with the jokes. We're going to type cold and dry, but everything is my favorite color. So I'm going to hit return, and then I want to save this. So I'm going to go to File, Save, and I call this Mars.txt. TXT. And click on Save. And yep. And then it should open this dialog box here. And I'll just say that so the like sort of theme of this lesson that's got like the sort of silly jokes is that they're like classic movie monsters that are trying to figure out what planet they want to establish their base on. And so this is their like sort of notes on different planets. So we will meet, I think, a mummy, Dracula, Wolfman. That might be it. Huh? I don't think so, but I could be wrong. Okay, is everyone here or have their file saved? Anyone not? Okay, so I'm gonna click on save. So one thing I forgot to mention, you can look for it later, is that when you've made unsaved changes to the file, it'll be red here and there'll be a little asterisk. And when the text is black, that means that there aren't any unsaved changes. Okay, so we made that change to the file. And what you might have noticed now is that in the Git pane here, now it has mars.txt. It didn't show up until we saved the file, right? So Git doesn't see anything to actually save changes, but now we have our question mark going on here. So again, Git doesn't know about it. It wants us to, if we want Git to deal with it, we have to tell it. So we will again click on the checkbox, and then we can click on the commit button to open the commit dialog box. And so we'll use a slightly better commit message now. Start notes on Mars. Oops, I can spell it right. Mars as a base. And like you'll notice that my commit message is almost as long as my changes. That's fine, right? I'm explaining what's going on. You know, your change might be just like a period or a semicolon because you're fixing a bug. But your explanation, like it might be a paragraph. That's okay. Okay, so I'm going to click on commit. And so changes are committed. I'm going to close that. And go back to our text editor. Anyone not back here? Okay. So now, like we've got our file, now we're going to actually make some more edits to it. The 2 moons may be a problem for Wolfman. So you can see here now the file name is in red and there's an asterisk there because I haven't saved it. And because I haven't saved it, it's not showing up in the Git pane yet. So I'll show you another way to save it, which is to click on the floppy disk. You all might not know what floppy disks are. That's what that little picture is. So now save my changes. It's showing up here. Now we're seeing something new. We have an M, right? Before we saw the green A and we saw the orange question mark. So the M there, the blue M is for modified, right? So it's saying, okay, you told me I'm responsible for this file. So I've taken care of like previous changes that you made, but now you've made a new change. You've modified the file. Now, like I need to know what to do with it. So I'm going to click on the commit button here to open the dialog box. And I'm going to, let's see, type my commit message, add concerns about effects of Mars's moons on Wolfman. Okay, and now I'll click on commit. And now I'm getting something different. So I can't remember if I mentioned this before, but Git actually has like, when there's a problem, the messages are usually pretty helpful. I can't tell you the number of times that I've gotten like a error message from Git. And I've been like, oh, that's weird. And then I Google it. I spend like 5 minutes like reading up on it. And then I go back and I figure out what the problem is and how to fix it. I go back and I actually read what it said and I'm like, oh, yeah, that's what I just spent 5 minutes trying to find, and it just told me that, right? So I'm going to read the message. Sometimes they're a little bit cryptic, but it says, changes not staged for commit. And then the other stuff, that's telling me what to do if I was using it from the terminal. So we don't need to pay attention to that, but it says no changes added to commit. So what does that mean? So we clicked on the commit button, but remember we have to stage changes before we commit. Two-step process. So it's saying you're trying to commit, but you haven't actually staged any changes, right? So until we click on this button here to stage it, it doesn't have anything to commit, and Git won't do what's called an empty commit, where like no changes have actually been made. So you can click on the stage button. You'll notice if you watch carefully that the M moved. This can be a little bit confusing, but this is, the M being here means there are modifications that aren't staged. And then the M being here on the left side, which is hard to tell right now, means that there are staged modifications. So now we can click on commit. And now it gives you like the kind of cryptic commit feedback. And click on close. This is the dialog window. That work okay for everyone? Any problems? Cool. Okay. So now let's add a little bit more text, but the mummy will appreciate the lack of humidity. And we can save that. And I'm going to click on the commit button here. And now I'm going to show you a few new things. One is that you can see here what I mentioned before. It's just showing in gray what was there before. Green is showing what's new. I didn't delete anything or change an existing line, so there's no red. The other thing that you might not have noticed before is this is showing me the unstaged changes. I can click on this little button here and it'll show me the stage changes, which is nothing because I haven't staged anything since I did the last commit. The other thing that you might not have noticed is that when I click on the checkbox here to stage it, it's going to flip from unstaged to staged because now I've staged these changes. So if I look at what's unstaged, there's nothing unstaged, no unstaged change. If I went now and like edited the file, those would actually show up as unstaged. And actually it would show up as another M here because I would have some modifications that were staged and some modifications that were unstaged, which is why there are those two spots. We're not going to do that right now. We will put in a commit message, discuss concerns about Mars's climate for mummy. Did I spell that right? Okay, I'm going to do a commit. And then I'm going to show you one other thing, which is that the dialog box is also, the commit dialog box also shows you the history, which I mentioned. So here, every once in a while, our studio Git acts funny, but so far it's being okay. So here it's showing me the commit message for each of the commits. And how long do I have to give? 5 minutes? Okay. I got 4 more minutes. Okay, so you can see each of the commit messages. You can see who did it, which was me. For each of you, it should say you. This is actually like a cryptographic hash, like we saw for the MD5 sums. It's a different algorithm, but each commit actually has its own cryptographic hash for like reasons I'm not going to get into. And then you can also see here, I told you, you can see what change you made at each of the commits, right? So I can go back and look at them. It's going to be funny for the first commit, but otherwise I can look at like the lines I added at each commit. So it's nice that it has this like record keeping. So if you're in the commit dialog box, you just click on history. There's actually another way, which is here, it's confusing. There's this history button, not to be confused with this history button, which is the art history, but this history button, which is the git history, will also. So the diff, the commit, and the history buttons all do the same thing. Although if you click on history, then it opens up the history first. But those buttons are a little bit redundant, but okay. So let's see about like kind of like a minor undo. I'm going to type here an ill-considered, oops, and I misspelled it. That's okay. Change, right? And I'm going to save it. And then I'm going to go to commit. And I'm going to look at that. I'm going to say like, oh, yeah, why did I make that change? That was a silly edit to make, or I don't like it, or like maybe I run my code and it doesn't work. So there are a couple of ways to undo this. Let's see, which one do I want to do? So we can actually click on this discard chunk button. I think what I'm gonna actually go for is this revert button. And that'll just go back to the previous committed version of the file. Sorry, the previous version. I think if I've staged things, it doesn't undo those. So if I do revert, it's going to ask me because it's going to undo it. Are you sure you want to continue? I'm going to say yes. So now those changes are gone. And if I go back and look at my original source file, it's back to the previous version. We have some other options for doing this. So let's add 2 new lines, no wind and a little bit dusty. And we'll save that. And then we'll open the commit window and see I'm all ready to commit. And then I think back to that movie, The Martian. Anyone seen the movie, The Martian, or read the book? So like, if you haven't, major plot line, important point at the very beginning of the movie is that there's a windstorm on Mars. And of course, we all know that everything in movies is always true. So I think no wind, and I think, could it be true? And I realized, oh yeah, like I've actually like heard about research from the like Mars rovers that there is wind, right? So I want to get rid of that. So hopefully RStudio will cooperate, and it will let you select just a line here. And when you click on discard line, it'll revert the line without reverting the other one. Sometimes this is a little finicky and doesn't work. Oh, it worked that time. So now I can actually commit that change, and then a little bit dusty because it is dusty, right? And so I'll put a commit message, notes about cleanliness on Mars. And I got to stage that. And I'm going to do commit. Okay. So it is 3:56 now. I could keep going for another 2 hours or more, but I'm getting dagger eyes from Richard. And also like, I probably couldn't keep going for another 2 hours because it collapsed. So what we do need to do though, is I need to tell you, so the rest of the notes here are available for you to use. Oh man, what happened to my QR code? What's up with that? Come on. It's there. Richard, I put it there. I swear, it's there and it worked. I checked it and the QR code's not working. Okay, wait, let me see if I can find the.
You go back to the schedule.
It's in there?
It's in there.
Okay.
The
Second one.
Yeah.
This one. Okay. I'm going to make it bigger. Okay. So please fill out the survey really quick. I think it should take you less than 3 minutes-ish. If you can do it now, we appreciate it. Like I said, well, actually, sorry. This is feedback that we use for not only reporting to NIH, but also for modifying things for next year. So people who come next year will appreciate the things that you tell us that we did right and things that you tell us we did wrong. And
it also, because we're getting this feedback, and so we may.
Yeah, actually, yeah, it might benefit you because we might make changes for like next week or the next few weeks or even sessions in the spring. Any questions other than that? Yep.
Yeah, so I'm trying to commit to last message, but I'm not seeing like there's nothing here.
I think you probably, so you can look at the history.
Okay.
So either you committed it, well, it means that you don't have like a change since the last commit. So you added the 2 lines and then, so it could be that you reverted both of them because there's another button there that's, let me see if I can leave the QR code up without. Disturbing things. So I'm just going to add 2 lines here. Okay. Now where's my commit? There. Yeah, if you squish it down, then the buttons don't say commit. Okay. So here you'll see there's a stage chunk and discard chunk, and it's sort of group line. So if you do discard chunk or stage chunk, it's going to do everything here. Actually, I'll just show you. Okay, so I know it's putting it all in one chunk. I don't know how it decides what's in a chunk, and then sometimes it'll separate it. Like there's some distance in the file away that it divides up chunks. But if you do stage chunk or discard chunk, which maybe is what happens, that it'll do all of the lines. If you want to just do an individual line, or you can do multiple lines, you can, like here, I can click on those 2 lines and do stage selection or discard selection, or I can just click on 1 line and say stage line or discard line. Does that help? Maybe. You can try typing it again, and I think that it must, because it's not there, it must be that it's like either you committed it or you discarded. Thank you.
IDR, fire.
Yep. Oh, and you know what I didn't do? I didn't explain cloning the repo.
That's true. Some people who attended last week would have gotten a hint of it, but not we'll just work on it.
Bad Josh.
Okay.
Normally I think of like, that's the thing I definitely have to do before we quit, but then I remembered this, I didn't remember that.
Yeah.
Are you Janice next time?
Yeah.
Yeah, I can only keep
You can only do
one thing, yeah. Any last questions, things on Zoom? Oh,
Yes.
yeah.
What is the function of the ignore button?
Sorry, what's the what?
The function of the ignore button?
Oh, yeah, sure. I can say that's part of the stuff that I didn't cover. So you can have files that you can have files that you don't want Git to pay attention to. And so one way to deal with that is that you just you see it here and you ignore it. The other way to deal with it, which is a better way, is I'll just show you an example. I'll make a little file here. Just type some stuff. I'll save it. I'll just call it stupid file txt and save it. So I don't necessarily want to get rid of this file, but I don't want Git to pay attention to it. So I can we'll do it. So it actually shows up here, and it also shows up in the commit window. So you can do it either one. So if I can click on that file to highlight it, I'm not clicking on it to stage, I'm just highlighting it. And then I click on ignore. It's going to add that file to there's a file that's hidden called a .getignore file. And so it'll add that file name there. And then if I save this change, now it's not, now that stupid file, it's still here. I can still see it if I look in the file browser, see, but Git's ignoring it. And actually now I've changed that file .getignore. So if you remember at the very beginning, we committed the .getignore file that the RStudio made automatically. And so here it's showing there are modifications to it. So if I look at that, you can see some other things that already got put there automatically by RStudio, and you can see this was added. So then you can actually, we could say, commit that change and say, updated .getignore with stupid. So that's what that's there for.
Thank you.
No problem.